Hey, and welcome to Minute Science Marvels, quick dives into the wonders of science. I'm Misha, and today we're talking about the massive fiery star at the center of our solar system, the sun. I had so many ideas for first episodes. Nuclear fusion, auroras, sunsets, the weather, all of them require talking about the sun. The sun is literally the center of our lives. It keeps us warm, gives us light, powers our planet's energy cycles, and even impacts our mood. But what is the sun really? We're going to break it down together and discover why the sun is not just cool, but actually hot, like 27 million degrees hot. Every episode, we'll dive deep into a topic, check out its real world impact, and then wrap it all up with some fun, mind blowing facts. So, to start off with, the sun is a 4.5 billion-year-old dwarf yellow star. It's a giant ball of glowing gas made mostly of hydrogen and helium. It's huge, about 109 times wider than the Earth and 330,000 times as massive. Sometimes people say the sun is the largest star, but it's actually just the largest in our solar system. Out there, there are stars that are much bigger. But to us, the sun is huge, containing over 99% of the total mass in our solar system. And all of that mass creates a huge gravitational pull. The sun holds all of the planets, moons, asteroids, and comets in orbit. Gravity pulls objects inward towards the sun. But the planets are also moving sideways at high speeds due to their initial momentum. They got this momentum when our solar system was initially formed. So these two forces balance out. The gravity pulls them in towards the sun, while their sideways motion keeps them moving forward, which results in a stable orbit. Objects in orbit follow an elliptical or an oval path due to the interplay between gravitational pull and their speed. So, the sun helps to keep us moving, but it's also essential to life on Earth because of the heat and the light that it gives off. How does it do that? The secret lies in its core, where nuclear fusion happens. I definitely want to do another episode just on fusion, probably fission too, but here's kind of the short version. At the core of the sun, the temperatures reach about 27 million degrees Fahrenheit, and the pressures are immense. The hydrogen atoms here are fused together to form helium. This process creates an incredible amount of energy, which radiates outward in the form of heat and light. Think about it like this. The sun is essentially a massive nuclear fusion reactor. Just side note, if you're thinking Chernobyl, that's fission. It's similar, but the opposite. Plants like Chernobyl split atoms, while nuclear fusion fuses or combines them. So this is a huge nuclear fusion reactor. At its core, the sun's immense pressure and the extreme temperatures make those hydrogen atoms able to be overcome. Those hydrogen atoms are able to overcome their natural repulsion, and then they're able to fuse into helium. This process releases a huge amount of energy, equivalent to the detonation of billions of hydrogen bombs every second. To put that into perspective, 600 million tons of hydrogen are fused into helium each second. So, 4 million tons of matter are being converted into pure energy, again in 1 second. So once this is produced, the energy begins its really long journey out because it has to travel through several layers of the sun. First, there's the radioactive zone. Energy here moves incredibly slowly as photons, particles of light, are constantly being absorbed and re-emitted by the dense plasma. Here, it can take thousands, even millions of years for the energy just to pass through this layer. Then it goes through the convective layer. In this outer layer, hot plasma rises while cooler plasma sinks, which creates convection currents that speed up the energy transfer process. Then there's the photosphere, the part that we see from Earth. Finally, the energy escapes as visible light, which we call sunlight. From this point, it travels at the speed of light, 8 minutes and 20 seconds to reach Earth. This energy powers nearly everything on Earth. Our weather, ecosystems, and even human life depend on it. The sun produces a staggering 3.8 times 10 to the power of 26 watts of energy. This is enough to meet Earth's energy needs for over 1 million years in just a single second of output. Nuclear fusion is wild. Sorry if you can hear my dog in the background. So we know how nuclear fusion produces energy on the inside. Let's move on to the surface of the sun, what we can see from Earth, the photosphere. The photosphere is literally cooler than the sun's core. It is 10,000 degrees, and the inside, like we said before, was 27 million degrees. That's 2,700 times hotter. To put that into perspective, it's like comparing something at room temperature to a raging fire, or that same raging fire to the heat of a lightning bolt. One fascinating feature about the photosphere is the sunspots. These are the darker, cooler areas that are created by intense magnetic activities. We can think about these as storms on the solar surface. They're most similar to hurricanes because of the eye, and they're massive. Some sunspots are so big they could fit multiple Earths inside of them. But the sunspots are just the start of the action. The sun's intense magnetic activity also causes solar flares, which are sudden, powerful bursts of energy that release massive amounts of radiation and charged particles into space. You can think of these as the sun's version of a volcanic eruption, but instead of molten rock, it's just pure energy shooting out at incredible speeds. Then there are the coronal mass ejections, or CMEs, which are like those solar flares that we just talked about on steroids. These giant explosions can hurl billions of tons of solar particles through space, traveling at speeds of up to 1 million miles per hour. To give you an idea of their power, one single CME can carry the energy equivalent of billions of nuclear bombs. Crazy. When these solar events interact with Earth's magnetic fields, they can trigger stunning auroras, those breathtaking light shows near the poles. But they can also cause chaos, disrupting satellites, GPS systems, and even power grids. The sun's magnetic field, which drives all of this activity, is constantly shifting, which makes the sun a dynamic and sometimes unpredictable ball of energy. Here is the section where I wanted to talk about the real life impacts of the sun. But to be honest, I struggled with this part because it's literally everything. The sun isn't just the center of our solar system, it's a source of life as we know it. Its heat and light sustain Earth's ecosystems, drive weather patterns, and fuel photosynthesis, which produces the oxygen that we breathe. Even our health benefits, as the sun helps our bodies produce vitamin D, the vitamin that's crucial for bone health, immune function, and even mood regulation. Side note, most of us have a vitamin D deficiency. But again, as we kind of touched on before, the sun's immense power isn't always gentle. Solar storms, which are caused by the flares or CMEs, coronal mass ejections, release enormous amount of energy and charge particles into space. Sometimes these storms can reach Earth, where they can disrupt satellites, knock out communication systems, and interfere with GPS navigation. In May 2024, semi-recently, a significant solar eruption disrupted the GPS systems in the American Midwest, which caused high-tech tractors to malfunction during planting season. In 2003, there were the Halloween solar storms, where solar activities caused radio blackouts, disrupted airline communications, and even impacted power grids. Even back in 1989, there was a CME that knocked out the power to the entire province of Quebec for over 9 hours. Now, we're in the midst of a solar maximum, which is a period of heightened solar activity as a part of the sun's 11-year magnetic cycle. This means auroras are more visible, but it also increases the risk of solar disruptions to technology. To address the challenges and deepen our understanding of the sun, there are several missions and programs that are underway. First, there's ESA's Proba 3 mission, which just launched last week, December 5th, 2024, if you're watching in the future. This one uses 2 satellites to create an artificial solar eclipse. This mission is studying the sun's corona, the outermost layer, in unprecedented detail. There's also NASA's Parker Solar Probe, which is going through the sun's outer atmosphere, and it's gathering vital data on solar winds and magnetic fields, which enhances the capabilities for producing, oh my goodness, it enhances the predictive capabilities for space weather. Sorry, brain fart. There's NOAA's Space Weather Prediction Center, which has data from GOES-19 and other missions. This Space Weather Center has real-time monitoring and forecasting on solar activity to protect technological infrastructure. Then there's also the Solar Orbital, which ESA and NASA are working together on. This mission is studying the sun's poles and inner heliosphere, which gives us insights onto solar winds and magnetic activity. These recent missions are increasingly important as we anticipate the heightened solar activity due to the current solar maximum. Understanding and predicting the sun's behavior is essential for protecting infrastructure, preparing for solar events, and advancing our knowledge of the cosmos. Whether it's ensuring that the satellites remain operational, or helping farmers in the Midwest, or even just letting us know where the auroras are at this time, studying the sun is crucial to our survival and our technological advancement. So, for the fun facts, my favorite part, the sun's life cycle. The sun is middle-aged. It's about 4.6 billion years old and has enough fuel to last 5 billion more years. After the sun uses up its fuel, it will expand into a red giant and then shrink into a white dwarf, a process that'll take billions of years. 4. The size and mass. The sun accounts for 99.8% of the total mass in our solar system. If the sun were hollow, you could fit 1.3 million Earths inside of it. With the solar winds, the sun loses about 4 million tons of materials every second, but again, because it's so huge, it's like nothing. The sun's structure. The sun has layers, kind of like an onion. This includes the core, the radioactive zone, the convective zone, the photosphere, the chromosphere, and the corona. 4. Shape and movement. The sun is almost a perfect sphere, but it's slightly flattened at the poles due to its rotation. The sun doesn't rotate equally. The equator, the middle, rotates faster. It takes about 25 days. And the poles, which are the outsides, take about 35 days. This is because it's made of plasma and not solid material. 4. Magnetic activity and cycles. Every 11 years, the sun's magnetic field totally reverses, which is why we experience things like solar minimums and solar maximums. Ooh, for sunlight and color, this was a new one for me. Did you know that sunlight isn't actually yellow? The sun emits all colors of visible light, but its peak emission is in the green part of the spectrum. We see it as yellow because of the Earth's atmosphere. And to recap, the sun is a massive ball of gas powered by nuclear fusion, constantly converting hydrogen into helium and releasing energy as light and heat. Its surface features, like sunspots and solar flares, result from complex magnetic activity. The sun drives life on Earth, but also poses challenges with its intense solar storms. I'm going to link some resources where you can dive in even further. So, thank you so much for watching. Like, subscribe, follow, download, do whatever to support the podcast. The video version is up on YouTube. The audio version is going to be on Spotify and Apple Podcasts, and then there's clips and shorts on TikTok and Reels. Yeah, that's everything. Thank you so much for listening, and I'll see you next Thursday. Bye.